The nearest star is more than 4 light-years from Earth. So if intelligent life exists around other stars, why has nobody crossed that distance to reach us? 4 light-years sounds almost close. It isn't. Light can make that crossing in a little over 4 years. A spacecraft cannot. A living crew cannot simply go there. A civilization has to build the machine, power it, shield it, guide it, repair it, and wait long enough for the journey to mean something. And that is where the alien question changes. The real problem is not just whether other civilizations exist. The real problem is whether any civilization can cross the space between stars for contact to become likely. Distance is enormous. Speed has a ceiling. Energy gets expensive fast. Dust becomes dangerous. Machines fail. Biology ages. And time keeps running. So maybe the silence is not telling us space is empty. Maybe it is telling us the islands are too far apart. By the end of this video, you will understand why the nearest star changes the whole alien contact question, why advanced technology does not make engineering disappear, and why a galaxy rich with life could still leave every civilization practically isolated from every other. So we start with the nearest star. Because if even the closest destination is almost out of reach, the whole galaxy starts to look less like a neighborhood and more like an ocean. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Known physics may not make alien visits impossible, but it may make the journey so hard that most civilizations never meet. They simply remain apart. Now, that idea matters because the modern imagination is pulled in 2 opposite directions at once. On one side is abundance. There are hundreds of billions of stars in our galaxy alone, and a vast number of planets. On the other side is silence. We do not see the sky full of traffic. We do not see obvious visitors arriving from nearby systems. We do not see the infrastructure of a crowded galactic civilization. The temptation is to treat these 2 facts as contradictory. If the universe is so large and so old, why would nobody have reached us by now? But that question often hides a dangerous assumption. It assumes that once intelligence appears, distance stops mattering. It assumes that advanced life eventually becomes almost magical, able to cross interstellar space the way aircraft cross an ocean. It assumes that enough time erases engineering, yet every serious discussion of interstellar travel begins in the same place. The laws of physics remain in charge. Advanced does not mean unconstrained. It does not mean free from energy budgets, impact hazards, material limits, communication delay, reliability problems, or the speed of light. So we need a different thought experiment. We stop imagining aliens as fantasy creatures with unlimited tools, and start imagining them as engineers trapped inside the same lawful universe as us. If they build ships, those ships need energy. If they move fast, they have to survive what they hit. If they want more than a one-time flyby, they have to slow down. If they want to coordinate across light years, they must endure long delays. And if they hope to meet another civilization, both societies must exist in the same place in time as well as in space. And once we frame the problem that way, the title starts to translate into something more careful. Not impossible in a mathematical sense. Impossible in the sense that many things are impossible in ordinary life. Not forbidden by logic, but blocked by the scale of reality. This distinction is easy to miss because science fiction trains us to imagine interstellar travel as the natural next step after space travel. First a moon base, then Mars, then the stars. But the jump from planets to stars is not a larger version of the same challenge. It is a different category. The distances are not a few times larger. They are catastrophically larger. The travel times are not inconveniently longer. They become civilizational. The hazards do not merely scale up. They transform the mission itself. And practical isolation is not the same as saying no machine could ever cross from one star to another. That would be too strong. A small probe is different from a crewed ship. A one-time flyby is different from arrival. A self-replicating probe is different from a biological civilization choosing to travel in person. Each version changes the engineering problem, but every version still has to pay the bill. The bill may be paid in energy, time, mass, reliability, shielding, navigation, or patience. It may be paid by a civilization that thinks on longer timescales than we do. It may be paid by machines rather than bodies. But it is never erased. That is why the stronger argument is not built on alien psychology. We do not need to decide whether another civilization would be curious, cautious, expansionist, indifferent, peaceful, or aggressive. Motives matter, but they come later. Before any motive becomes a mission, it has to pass through the physical world. A civilization can want to visit Earth. It can have reasons to explore. It can even possess technology far beyond ours. But a desire is not a trajectory. A plan is not a spacecraft. An intention does not cancel distance. So the useful question becomes narrower and more serious. What must be true for interstellar arrival to become routine enough that we should expect visitors? How cheap must energy become? How reliable must machines become? How long must institutions last? How well must a craft survive dust, radiation, cold, and delay? And how many civilizations must overlap in time for any of this to matter? Now we are no longer asking a loose mystery question. We are building an engineering frame. We can ask what has to be crossed, what has to be survived, what has to be accelerated, what has to be slowed down, and what has to remain coordinated across years or centuries of delay. Here is the important part. These barriers do not arrive one at a time, politely waiting their turn. They stack. A faster ship needs more energy, but higher speed makes dust impacts worse. More shielding helps with impacts, but shielding adds mass. More mass demands more propulsion. More propulsion creates more heat. More heat demands more radiators, which add more mass again. So practical isolation is not one locked door. It is a corridor of doors. Opening one can make the next one heavier. A civilization might solve parts of the problem brilliantly and still find that the full chain remains punishing. This is why the absence of obvious visitors does not have to mean absence of life. It may mean the opposite of what our instincts suggest. The galaxy may contain many minds, many histories, and many technologies, but still very little traffic between them. Not because nobody looks up, because looking up is much easier than crossing the dark between stars. And that changes the emotional shape of the question. The silence is not automatically eerie. It is not automatically suspicious. It may simply be what a vast, lawful universe sounds like from the inside, when every possible neighbor is separated from every other by distances that punish even very good technology. And we should be fair in a particular way. Some arguments about alien visitation begin from certainty and work backward toward evidence. We need to do the opposite. We begin with what is actually known, the physics, the distances, the engineering literature, and let the conclusions follow from that. The goal is not to prove a comforting conclusion, nor a scary one. The goal is accuracy. The relevant literature here is not science fiction, and it is not fringe speculation. It includes NASA interstellar mission overviews, serious academic roadmaps for interstellar propulsion, peer-reviewed reviews of the interstellar medium, engineering studies of dust hazard and shielding, SETI technosignature research, and careful statistical analyses of civilizational overlap. People with engineering training and professional stakes in accuracy have thought carefully about these problems. Their conclusions tend to be conservative. Their conservatism is not timidity. It is the product of taking the arithmetic seriously. And what we find is that the arithmetic, when taken seriously, does not produce a simple answer in either direction. It does not prove that aliens have definitely visited, and it does not prove that the universe is definitely empty of other intelligence. It produces something more precise and more interesting than either extreme. It produces a picture of a universe where the barriers to interstellar contact are very high, where those barriers compound rather than cancel, and where we should expect to find ourselves in a condition of effective isolation regardless of what may or may not exist elsewhere. Understanding that picture clearly does not diminish the wonder of the universe. In many ways it sharpens it. So we begin with something simpler than alien motives, secret technologies, or speculation about intent. We begin with the nearest star, because distance comes first, and because every serious answer has to take that scale seriously. Now, the nearest star system to the Sun is Proxima Centauri, about 4.24 light-years away. Those numbers are familiar enough that they can start to feel almost decorative. 4.24 light-years. It sounds precise, but precision can disguise strangeness. A light-year is the distance light travels in 1 year, and light is not slow. Light covers about 300,000 kilometers every second. It circles Earth more than 7 times in a second. It reaches the Moon in a little over 1 second. It reaches the Sun in about 8 minutes. And even at that speed, the nearest star beyond the Sun is more than 4 years away. That means the baseline fact of interstellar life is already extraordinary. Even information cannot cross the gap quickly. If a civilization around Proxima sent a message today, and we answered the moment we received it, the round-trip conversation would take more than 8 years. That is for the nearest star, not a star on the other side of the galaxy. The nearest one. Now set beside that the speed of the machines humans have actually built. Voyager 1, one of the fastest outward-bound spacecraft ever launched by our species, travels at roughly 17 kilometers per second relative to the Sun. That is an amazing achievement by planetary standards. It is also essentially motionless by interstellar standards. After 37 years of powered travel followed by continued coasting, it has barely entered the fringes of interstellar space. Compared with light speed, Voyager moves at less than 0.006% of c. If Voyager were aimed toward the nearest stars, the journey would take on the order of 74,000 years. 74,000 years is difficult to hold in mind. It is longer than recorded history, longer than agriculture, longer than cities, writing and metalworking combined. If a machine had been launched toward Proxima at Voyager-class speed around the time our species was painting caves and entering the final phase of the last ice age, it still would not be there. So distance is not a minor inconvenience waiting to be engineered away. Distance is the central fact. Distance is the main event. It controls every other sentence that follows. But sometimes numbers like these slide past without landing. So let us perform a different kind of sanity check, one using the distances we actually know, rather than the ones we only describe. Think about our own solar system. We speak casually about exploring space, yet even here, where the Sun binds everything into one local family, the distances already dominate mission design. The Moon is close by cosmic standards, and even that journey required a concentrated national effort at the height of geopolitical urgency. Mars is close enough to discuss seriously for crewed missions, yet the transit time, life support demands, radiation environment, and surface hazards make it one of the most technically ambitious goals we have ever set. The outer planets require robotic missions that take years to arrive. Deep space communication already involves significant delays. Voyager 2 data from the outer solar system takes roughly 16.5 hours to reach Earth, and that is still inside our own local neighborhood. Here is the critical point that Sanity Check reveals. We have not yet made routine settlement of our nearest planetary neighbors look easy. We have not produced a civilization in which the asteroid belt is ordinary traffic, or the moons of Jupiter are familiar ports. And that is all inside one star system, where the light delay is measured in minutes or hours, where the Sun provides a shared gravitational center, and where the total travel distances are tiny compared with the gap to another star. Sometimes discussions of alien arrival skip too quickly from perhaps they are more advanced than us, to therefore perhaps interstellar travel is routine for them. But if we treat engineering seriously, then the leap from planetary spaceflight to interstellar travel should not be imagined as a single smooth curve of improvement. The space between those two achievements may be larger than the space between sailing and orbital mechanics. Imagine explaining to someone in the age of wooden ships what it would take to land on the Moon. The answer would not be just build a somewhat better boat. The answer would require an entirely different understanding of nature, materials, energy, guidance, chemistry, mathematics, and industrial coordination. Interstellar travel may represent a jump even larger than that. Look at the numbers this way. The solar system extends roughly 40 or 50 astronomical units to the outer Kuiper belt. Proxima Centauri sits at about 268,000 astronomical units. The nearest star is not a few times farther than our outermost planet. It is more than 5,000 times farther. That ratio does not describe a slightly longer journey. It describes a different problem entirely. There is a habit in popular discussion of treating the galaxy as locally accessible because it is full of stars. Yet abundance does not imply closeness in any useful engineering sense. The Milky Way contains enormous numbers of stars, but they are spread across a structure about 100,000 light-years wide. Even within our local neighborhood, the separations are immense. A few light-years here, 10 light-years there, dozens beyond that. To a radio astronomer, these are nearby systems. To a mission planner, they are not nearby at all. Now what if we imagine something far faster than Voyager? Serious interstellar studies often use a probe speed of about 1/10 the speed of light, or 0. 1c as an ambitious long-term target. That number sounds almost triumphant until one remembers what it still implies. At 0, 1c, a probe takes roughly 40 to 50 years to reach the nearest star, depending on mission design and what counts as arrival. This is not a civilization hopping casually between systems. This is a half-century mission to the nearest possible destination for a small robotic payload under an extremely demanding propulsion scenario requiring infrastructure no civilization has yet built. And that is the optimistic version. Once you move beyond the nearest stars, or once you require a heavier payload, or once you want to do more than rush through on a flyby, those decades begin to stretch again into generations. And here is something worth sitting with as a mental image. At 0, 1c, a mission to a star 30 light-years away, not across the galaxy, just 30 light-years, which encompasses only a very small neighborhood around the Sun, would take 300 years in transit. 3 centuries. Every living person connected to the mission would be long dead before the probe arrived. The institutional structures that funded it would almost certainly have transformed beyond recognition. The questions the mission was designed to answer might have been answered by other means, or replaced by entirely different questions. The civilization that receives the data, if it ever does, is separated from the civilization that launched the probe by 3 centuries of history. Think about what 3 centuries means in practice by looking backward. 3 centuries before this moment takes us to the early 18th century, before the Industrial Revolution, before the germ theory of disease, before the discovery of oxygen, before the United States existed, before almost every institution we presently regard as foundational to modern civilization. The idea that any institution of that era could have maintained custody of an active scientific mission all the way to the present, with coherent goals, funding, and interpretive capacity, is nearly impossible to take seriously. Yet that is what a 300-year mission to a star 30 light-years away would require of its sending civilization, or of whatever civilization follows it. The galaxy looks different when viewed through travel time. It stops feeling like a landscape and starts feeling like an archipelago spread across dark, cold ocean. Every island may exist, many may even be inhabited, but the water between them is so vast that the default condition is independence. The archipelago metaphor carries further than it first appears. On Earth, archipelagos have in some cases produced remarkable maritime cultures, communities that developed boats, navigation and trading networks precisely because the sea was omnipresent. You could call that an optimistic reading of separation. Isolation produces ingenuity, and ingenuity produces tools for crossing water. But even the most remarkable maritime civilizations of history operated over distances that can be described in days, not millennia. The Pacific, the largest ocean on Earth, can be crossed in roughly 14 hours by modern jet aircraft. The analogous ocean between the Sun and Proxima Centauri, crossed at the speed of those same aircraft, would take roughly 5 million years. The scale does not merely multiply the maritime challenge, it replaces the maritime challenge with something categorically different. And there is a subtlety worth pausing on when we discuss the nearest star. Proxima is nearest in the sense that it is the smallest entry in a distance catalogue, but the next entries are not close to Proxima either. Alpha Centauri A and B, the other members of the same triple star system, are also around 4.24 to 4.37 light-years away. Beyond that cluster, the next candidates are Barnard's star at 5.96 light-years, Wolf 359 at 7.86, and Lalande 21185 at 8.29. The local stellar neighborhood is actually sparse. These are not a dense cluster of nearby ports. They are widely spaced targets, each requiring its own mission, each adding its own light-year gap beyond the one before. This matters because sometimes the existence of many stars is used to suggest that interstellar travel is feasible in aggregate, as if sheer number compensates for individual distance. But the number of stars does not reduce the distance to any one of them. The galaxy contains hundreds of billions of stars. Those stars are arranged across a structure roughly 100,000 light-years in diameter. The average separation between stars in the galaxy is several light-years. No star is close by the standards we have been using. Every destination requires the same basic argument from scratch. Now, one more sanity check deserves attention. Our own civilization has been sending robotic missions beyond Earth for less than 70 years. In that time, we have explored much of the solar system with Flyby probes, entered orbit around multiple planets, landed on the Moon, Mars, and several smaller bodies, and sent 2 spacecraft into the interstellar medium. This is genuinely impressive by any reasonable measure of technological progress. It is also profoundly limited by interstellar standards. Every mission we have managed, including the most ambitious ones, operates within a few light hours of the Sun at most. The only objects we have successfully placed on course for interstellar space are moving so slowly that they will not complete interstellar crossings within any conceivable human institutional timeframe. We are not saying this to diminish the achievement. We are saying it to calibrate expectations honestly. If a civilization that has been spacefaring for 70 years is still entirely contained within its local star system, the argument that any sufficiently advanced civilization would naturally spread between stars becomes harder to sustain as an obvious default. There is a useful discipline in engineering that goes by the name of requirements traceability. Every design decision is connected back to a specific requirement, and every requirement is connected back to an actual mission need. When that discipline is applied to interstellar travel, the first question is not how do we go faster, but what exactly does the mission require, and what does satisfying that requirement cost? Apply that question to an alien mission to Earth, and you quickly discover that the requirements multiply faster than the solutions. Not because the universe is malicious, because that is what requirements traceability looks like when the problem is genuinely hard. This alone already weakens the casual argument that someone should have shown up by now. To say someone should have arrived assumes that star travel is eventually cheap enough, safe enough, and valuable enough to become common. But the first lesson of the nearest star is that the burden of proof runs the other way. The universe begins with a presumption of separation, and notice how the burden of proof point interacts with the intuitions most of us bring to this question. Popular culture has spent decades imagining alien visitors as a fairly natural occurrence. Strange, perhaps, but imaginable. Alien ships in our skies, alien intelligence probing our civilization from above. The question is not whether aliens could exist. It is whether the physics and energy and time required to get from there to here are routinely paid, and that question has a different flavor than simple wonderment at the size of the universe. You would not be surprised if 2 isolated communities in a vast wilderness had not found each other yet, even if you knew both existed. You would not call their non-meeting a mystery, you would call it geography. The interstellar case is the same, extended by an enormous factor. The surprise would not be that we have not been visited. The surprise, requiring the most explanation, would be if we had, and once that is clear, the next hope usually appears. Perhaps, we tell ourselves, the answer is simply to go much faster. Perhaps scale is only a problem until technology matures. But this is where interstellar travel stops being a matter of better engines and starts colliding with a deeper rule. Before we move on, there is one more thing worth naming explicitly. We speak casually about interstellar distances as if they are simply very large versions of familiar large distances. But there is a way in which this framing misses something about what interstellar space is as a physical environment, not just as a gap to cross. Interstellar space is not merely the emptiness between stars. It is a qualitatively different environment from anything inside a stellar system. The heliosphere, the bubble of charged particles blown by the sun's solar wind, protects everything inside it from much of the galactic cosmic ray flux that permeates the rest of the galaxy. Beyond the heliopause, that protective bubble ends. The radiation environment, the dust environment, and the magnetic field environment are all different. The temperatures are different. The composition of any medium encountered is different. We tend to think of space as empty, which makes interstellar space sound simply like more space. But it is more usefully thought of as a transition into a regime that our species has barely sampled with any instrumented spacecraft. Voyager 1 and 2 are the only human objects that have operated beyond the heliopause, and they are doing so at extremely low speeds, with minimal instrumentation still functional after decades of operation. What we know about the deep interstellar medium comes largely from astronomical observation and theoretical modeling, rather than from direct in-situ measurement. The environment that any interstellar mission must traverse for the bulk of its journey is, in the literal sense, poorly characterized from direct engineering experience. This matters because when mission designers assume properties of the interstellar medium for design purposes, they are working with models whose accuracy has limited empirical validation over the relevant spatial scales. The known unknowns are real, and the environment that the mission must cross is not merely large, but genuinely alien in composition, radiation level, and medium properties, compared to what we have built systems to operate in before. So the distance is not just a time and energy problem. It is also a design environment problem. Engineers must design for a regime they know less well than they know Earth orbit, less well than they know the inner solar system, less even than they know the outer solar system. This is one reason why extending our robotic reach into the interstellar medium, even at slow Voyager-like speeds, remains scientifically and technically valuable. Each data point from beyond the heliopause is a small act of empirical calibration for a design environment that any interstellar mission would have to inhabit for most of its operational life. Now, if distance is the first barrier, relativity is the second. It prevents the most obvious solution from becoming a solution at all. No material object can simply accelerate past the speed of light and turn interstellar travel into an afternoon commute. Light speed is not just a difficult target. In modern physics, it is a structural limit built into the way spacetime behaves. That single fact reshapes the entire problem. It means every interstellar mission remains trapped inside long durations. It means even the most sophisticated civilization must confront the reality that the stars are not merely far away, but far away in a universe with an enforced speed ceiling. You can approach that ceiling. You can never casually ignore it. This is where time dilation often enters the conversation as a kind of loophole. And it is true that relativity does something counterintuitive. For travelers moving at very high fractions of light speed, onboard time can pass more slowly relative to the outside universe. In that sense, a journey that takes decades or centuries in an external frame may feel shorter to those on the ship, but this does not solve the full problem. Treating it as a solution usually confuses one perspective for the mission as a whole. First, time dilation becomes strongly helpful only when speeds are already extremely close to light speed. Reaching those speeds is itself part of the problem. Getting to 0, 5c, 0, 9c or higher does not come free. The energy required to accelerate mass grows steeply as velocity approaches light speed. The same physics that produces the dilation also makes the acceleration more expensive per unit of speed gained. You cannot collect the benefit while evading the cost. Second, time dilation does not pay the energy bill. It does not remove the need to accelerate mass to relativistic velocity. It does not erase the heat, shielding, navigation and braking demands that arrive with such speeds. It does not make the craft safer. If anything, higher speeds intensify the hazards. Third, time dilation does nothing for the destination civilization, which still waits in ordinary external time. Imagine a crew somehow crossing interstellar space at a velocity high enough that the journey feels manageable on board. From the traveler's perspective, perhaps only a limited number of years pass. From Earth or the target system, far more time may pass. Time dilation can soften the subjective duration for travelers, while leaving the basic fact of separated civilizations intact. If your concern is not only whether travelers can endure the trip, but whether two societies can interact, exchange, respond, and remain synchronized, then time dilation is not an escape. It is only a change in bookkeeping. There is another subtlety here. Even if one grants an extraordinarily advanced propulsion system, relativistic travel makes every other engineering problem harsher. At higher speeds, impacts become more dangerous, precision matters more, and acceleration itself becomes harder to survive biologically and structurally. The closer you push toward light speed, the less forgiving the mission becomes. This is one reason serious scientific discussions of interstellar travel are typically conservative in tone. They do not talk as if faster travel simply waits on better batteries. They talk about deep trade-offs. Very high speed can shorten transit time, but only by forcing the craft into a more extreme regime of energy, shielding, and infrastructure. What looks like a shortcut is actually an exchange. You buy fewer years with more violence, and here is a point that tends to be underappreciated. The exchange is not merely between speed and danger. High-speed travel also compresses the timeline available to detect and respond to unexpected obstacles. At low speed, a craft has more time to survey what lies ahead, adjust its course, and act on new information. At very high speed, the approach rate to any object in the path is so extreme that reaction time essentially disappears. Navigation systems must make decisions based on information collected at vast distances in advance, which means they must be accurate enough to predict clear corridors years ahead of the craft's actual position. Any navigational error that small machines simply cannot detect and correct in advance becomes a mission-ending event. Speed does not just intensify the physics of impact, it shrinks the margin for adaptation. Relativity also preserves another form of isolation that is sometimes overlooked. Communication can never outrun light either. So even if a mission is underway, no real-time coordination exists across interstellar distances. There is no joystick control from home. There is no quick consultation. Any complex operation must be carried by local autonomy, predictions made years in advance, and tolerance for long periods of uncertainty. The travelers and the senders are separated not only by space, but by causality. Think about what that means for civilizational coordination. If a civilization imagines sending ships to multiple systems and maintaining any kind of unified command, the communication delay makes that fantasy structurally impossible. Every colony or outpost becomes semi-independent almost immediately after it gets far enough away. Instructions from home arrive stale. Emergencies cannot be reported and answered in time. Any political, scientific, or social coordination must work across years-long delays in every direction. That is not an empire in any historical sense. It is a scattering of isolated outposts connected by very slow letters. So relativity does not merely prevent faster-than-light shortcuts. It changes the social meaning of distance. It ensures that separation remains real, even if travel becomes possible in principle. The stars do not become roads. They become long, slow commitments to futures neither end can fully control. Here is a thought experiment worth holding. Imagine two civilizations each capable of achieving 0.9 times the speed of light, which is already an extraordinary and perhaps unrealistic technical achievement. At that speed, a crossing from one side of the galaxy to the other would still take on the order of 100,000 years in outside reference time, even though the travelers might experience a shorter duration aboard. Now imagine they want to communicate before they travel. Their messages move at light speed, meaning 100,000 years minimum round trip for a conversation. By the time an answer could arrive back at the origin, every living person who sent the original question would be thousands of generations in the past. Their institutions, language, and culture would be unrecognizable. This is not speculation about alien psychology. It is a consequence of the speed of light applied to real distances, and it means that even a civilization capable of very fast travel still lives in a universe that is structurally non-interactive over galactic scales. Coordination between distant civilizations is not merely difficult, it may be meaningless in the ordinary social sense before either party has changed beyond recognition. Closer to home, the light travel time between Earth and the nearest few star systems runs between 4 and 10 years. A mission sent to Proxima Centauri at 0. 1C takes about 40 to 50 years to arrive. If the target civilization detects the incoming probe, processes what it means, and replies, either by sending back a signal or launching its own probe, the reply at the same speed takes another 40 to 50 years to return. This single exchange, send, receive, respond, receive the response, spans roughly a century. No human institution has maintained a coherent single mission objective for a century without significant change of priorities, funding structures, or interpretation of goals. For distant stars, the timescales are far worse. Now consider what the speed limit does to any notion of a galactic civilization as a coherent entity. Something with shared values, shared decisions, shared governance. Even if instantaneous communication were possible, a galaxy-spanning civilization would require all its member parts to act on information that could be 100,000 years out of date on any given axis. In reality, all information travels at light speed, so every part of such a civilization exists in effective isolation from every other part, except over very long timescales. Galactic empires and federations are not merely politically unlikely, they are causally incoherent under the physics we have. None of this stops individual civilizations from having ambitions, but it does describe what the universe actually allows. The speed limit is not a setback that better engineering overcomes. It is a structural feature of space-time that every civilization, regardless of advancement, must accommodate. And now the next question appears. Suppose we accept the speed limit. Suppose we aim not for fantasy, but for a sober target like 1/10 the speed of light. What would it actually take to push a machine, let alone a habitat or a crew, to that kind of velocity? This is where interstellar travel becomes less like exploration and more like an argument with energy itself. But before we leave relativity entirely, we should hold one more implication in mind. The same framework that produces the speed limit also imposes a communication structure on the universe that changes what we mean by civilization. Every society that exists at a large enough spatial scale is, in a physical sense, living in its own local past relative to every other part of itself. A civilization spanning 100 light years knows what is happening at its edges only in a 100-year-old snapshot. It cannot govern, respond, or coordinate on shorter timescales than light allows. This means that any large-scale civilization in this universe is not unified in the way that the word civilization usually implies. It is a loose, asynchronous scattering of communities that share an origin but inevitably diverge as communication lags compound. This matters for the visitation question because it shapes what we should expect an alien civilization to look like if it were capable of interstellar efforts. We imagine a unified civilization deciding to visit Earth. But any civilization large enough and old enough to have developed interstellar capacity may have already fragmented into something closer to an ecology of successor groups, each with different priorities, different technologies, and different relationships to whatever interstellar infrastructure the original civilization developed. They is not necessarily a coherent agent capable of unified decisions about Earth. They may be thousands of semi-independent communities across dozens of star systems, related by origin but divergent by the constraints of light speed delay over centuries. And there is a practical point hidden in this. When we ask whether an alien civilization might send a mission to Earth, we are often implicitly imagining something like the Apollo program, a unified societal decision made at the civilizational level aimed at a particular goal. But for any civilization significantly older and more dispersed than ours, the decision structure is probably not Apollo-like. It is probably more like asking which of the thousands of semi-autonomous groups with varying levels of technological capacity and varying levels of interest in Earth-like planets would choose to spend the resources required for an Earth-targeted mission, and then, given that choice, how many of those groups would successfully complete it? The answer might still be non-zero, but it is a very different question than the one most alien visitation discussions implicitly ask. Now, to move a payload to useful interstellar speed, you must give it kinetic energy. That sentence sounds almost too simple to be important, but it is the heart of the matter. The faster you want to go, and the more mass you want to move, the larger the energy requirement becomes. Interstellar travel is not just a propulsion problem. It is an energy acquisition, energy handling, and infrastructure problem on a scale much larger than most popular depictions allow. For robotic probes, researchers sometimes discuss 0.1c as an ambitious long-term target. That is already an extraordinary regime. Concepts like directed energy propulsion exist precisely because ordinary rockets are nowhere near enough. If you keep the payload very small, and if you move the energy source off the craft and into a huge external beaming system, then you can at least sketch a path toward relativistic probes. The Lubin roadmap for interstellar flight proposes exactly this architecture. Enormous laser arrays stationed near the Sun, beaming energy outward to push Gram-class wafer probes to relativistic speeds. Notice what this implies. The optimistic scenarios do not begin with giant vessels carrying cities. They begin with wafer-scale spacecraft, Gram-class payloads, enormous beaming infrastructure, and mission profiles stripped down to what physics might possibly permit. The reason these concepts exist is not that interstellar travel is easy. It is that the ordinary approach fails so badly that we must redesign the entire architecture around minimal mass. That reframing is significant in its own right. When physicists and engineers engage with interstellar travel seriously, they are not starting from a baseline of ordinary rockets and asking how to make them go faster. They are asking what the minimum conceivable mission looks like under real physics, and then working upward from there. The result is always a stripped-down, constrained architecture that bears little resemblance to what popular imagination pictures when it thinks of ships crossing from star to star. The distance between the optimistic proposals of serious researchers and the casual visitation scenarios in popular culture is not a matter of detail. It is a matter of the basic framing of what a real mission looks like, and we should be honest about what this implies. If we, as a species that has been watching, measuring, and planning space missions for decades, cannot yet describe a crude interstellar mission in terms other than theoretical aspiration, we cannot simply assume that another civilization would have solved the same problem as a matter of course. The fact that we keep returning to gram-scale probes and wafer architectures as our most defensible near-term interstellar concepts tells us something real about where the hard limits sit. So when we ask whether an alien civilization might have arrived at Earth, we are implicitly asking whether that civilization managed to cross not one barrier but several, each of which the most serious researchers in our own tradition continue to describe as extraordinarily difficult. And even then, a fast flyby probe is not the same as useful presence. A small payload moving at relativistic speed through another system may collect data if it survives, but it is not the same as arriving in a way most people imagine when they think of visitation. Mass is the merciless variable here. Every extra kilogram must be accelerated. Every added shield must also be accelerated. Every extra system to keep a crew alive adds still more mass, which demands still more energy, which in turn may require still more structure. The penalties compound. This is why the distinction between probe missions and crewed missions is not a matter of degree. It is a matter of category. A robotic probe can be tiny, disposable, purpose-built, and indifferent to comfort. It does not need oxygen, water recycling for generations, medical systems, psychological stability, or room to survive biologically. It does not care about governance. It can accept high risk. It can be optimized almost entirely for mass efficiency and mission narrowness. A crewed craft cannot do any of that. The moment living beings enter the picture, the spacecraft becomes not merely a vehicle, but an environment. It must shelter metabolism, regulate temperature, manage waste, provide redundancy, absorb radiation, endure failures, and preserve living organisms for enormous spans of time. To say that such a mission is harder than a probe mission almost understates the case. Here is one way to feel the weight of that difference. Consider the difference between designing a probe that must function for 50 years and designing a habitat that must sustain human life for 50 years. The probe can be made dormant between events. It does not require food, water, or oxygen. It does not need social stability or psychological well-being. It can survive enormous temperature swings. It can lose subsystems and recover data from whatever remains. Failure can be tolerated in degrees. A human habitat cannot compromise on any of those dimensions. It must deliver the right atmospheric mix continuously, manage CO2 continuously, maintain temperature within a narrow biological range, supply calories and water reliably, provide medical capability for injuries and illness that arise without warning, maintain enough structure to prevent catastrophic depressurization, cycle waste, and somehow address the psychological reality that long-duration isolation in a small pressurized environment has genuine physiological and cognitive effects that are not simply matters of attitude. The International Space Station has teams of engineers on the ground, regular resupply missions, continuous communication with mission control, and crew rotations averaging 6 months. A one-way interstellar mission deprives the travelers of every one of those support structures. Long-duration spaceflight data collected from Earth orbit, from missions beyond low orbit, and from simulations of confined environments consistently shows that the biological and psychological demands of isolation and confinement are real engineering constraints, not footnotes to be resolved by crew selection. Bone density loss, cardiovascular deconditioning, vision changes, radiation effects on cellular repair, and the documented psychological toll of extended confinement are all genuine concerns. These are not problems invented by pessimists. They are problems discovered by the medical and operations literature on crews who have already done extended spaceflight at far more forgiving distances. Now extrapolate those concerns from 6 months to 5 decades, strip away the resupply missions, the communication access, and the possibility of emergency return, and you begin to understand why the gap between a robotic interstellar probe and a crewed interstellar habitat is not a scaling problem. It is a category difference, but mass is only the first penalty. Heat is the second, and it is often left out of popular discussions. Any real machine that processes power, changes velocity, runs life support, computes autonomously, or shields itself against a hostile environment, must also manage waste heat. In ordinary discussions of rockets, heat sometimes feels like a technical footnote. In space, it is a governing constraint. A spacecraft cannot simply dump heat into the air. It must radiate it away through dedicated surfaces. As power use rises, thermal management becomes architecture. A high-performance interstellar mission is also a high-burden thermal mission. Faster travel demands more power. More power demands more cooling. More cooling demands more structure. More structure means more mass. More mass deepens the propulsion burden. The loops close around each other. Now add redundancy, because a mission intended to survive for decades or centuries cannot rely on a single vulnerable chain of components. Redundancy means backups, spare pathways, reserve systems, self-monitoring, fault recovery, and sometimes self-repair. All of those increase complexity. Complexity may improve resilience in one way while creating new failure modes in another. A small robotic probe can sometimes solve this by accepting mortality, cheap enough to swarm, simple enough to lose. But a mission meant to arrive in a meaningful, durable way cannot be so carefree. This is where the concept of mission brittleness becomes important. Brittleness is what happens when a system is optimized for nominal performance in known conditions while accumulating sensitivity to unexpected conditions. Very capable systems can be very brittle. The more tightly designed a machine for its primary purpose, the more likely it is to fail ungracefully when something off-nominal appears. Long-duration interstellar missions are ideal environments for off-nominal events. A journey measured in decades crosses through conditions that no pre-launch test can fully simulate. Encountered conditions will differ from expected conditions. The mission architecture must be robust to those deviations in a way that short missions can afford to ignore. History of robotic missions even within our solar system illustrates this. Missions have failed because of software unit conversion errors, because of stuck actuators, because of communication timing errors, because of micrometeorite damage, because of thermal behavior that deviated slightly from models. Each of those failures occurred within years, not decades of launch. Each occurred close enough to Earth that at least some corrective communication was possible. Each occurred in an environment far more forgiving than interstellar space. The lesson is not that missions always fail. It is that the failure modes of long missions are difficult to fully anticipate, and that the farther from home the mission operates, the more critical local fault tolerance becomes. This is also where vague appeals to alien advancement become misleading. Perhaps another civilization is far beyond us technically. Fine. But being advanced does not abolish the cost of accelerating mass. It does not erase waste heat. It does not remove the need for materials to endure stress. It does not make breaking free. It does not guarantee that a civilization will commit a substantial fraction of its industrial capacity to sending heavy payloads across light years. Think about what it would take to launch something at 1 c that masses more than a gram. The kinetic energy of 1 kilogram at 1 c is about 450 terajoules, equivalent to roughly 100 Hiroshima-class explosions delivered to 1 kilogram of payload. For 10 kilograms, multiply by 10. For a crude vessel massing perhaps tens of thousands of kilograms, the numbers become so extreme that they require a civilization to dedicate energy on the scale of planetary economies to a single launch. Advanced does not mean that math stops working. It means engineering those numbers more cleverly, but the numbers remain. And there is another cost hidden inside the energy problem. Speed makes space more dangerous. If you pour enough energy into a craft to turn the journey from millennia into decades, then you also create a machine that meets even tiny particles with extreme violence. In that sense, propulsion and survivability are not separate problems. They are two sides of the same bargain. The more ambitious the speed target, the more aggressively the craft must be shielded. The more mass devoted to shielding, the more energy required for acceleration. And the faster the craft, the less time it has to detect and dodge objects in its path. Propulsion and hazard cannot be solved sequentially. They must be solved together. Even the most optimistic interstellar proposals achieve plausibility by restricting ambition. Small probes, not large transports. Flybys, not deep operational arrival. Highly specialized missions, not normal traffic. That pattern itself tells a story. The universe does not offer an easy route to moving large, fragile, complicated things between stars. And here is the hidden message in that pattern of restricted ambition. The Breakthrough Starshot Initiative, with its gram-scale probes and enormous laser arrays, is one of the most seriously funded and publicly credible proposals for actual interstellar mission development ever undertaken. Its proponents are serious physicists and engineers. Its concept has survived public scrutiny from the astronomical community. And what it proposes, as an ambitious eventual target, is a wafer-thin chip accelerated to a substantial fraction of light speed, aimed at the nearest star, with no ability to slow down at the destination. That is not the interstellar travel of popular imagination. That is what the frontier of realistic ambition looks like, when physicists are in charge of the framing. What does it tell us that the most credible, serious proposal in this space is a disposable chip on a fly-through? It tells us that the distance between conceivable under physics and achievable with plausible future engineering is very large, and that even the narrow end of that gap produces only the most minimal form of interstellar presence. Everything beyond that minimum, heavier payloads, slower speeds, deceleration, crude missions, extended operations, sits at the far end of a scaling problem that does not improve easily. And if we are being careful, we should note that even the minimal concept faces real engineering challenges. The laser array required for the Starshot proposal would need to be kilometers in scale, built and operated in space, coordinated with extraordinary precision, and capable of delivering sustained power output of hundreds of gigawatts during the acceleration phase. These are not trivial requirements. They represent a substantial fraction of humanity's current total electrical generating capacity, focused on a single point for a short time. Building and maintaining such infrastructure is within theoretical reach for a more capable future civilization, but it is not something that arrives incidentally as a byproduct of ordinary technological progress. It requires deliberate, focused, expensive development aimed specifically at interstellar goals. The fact that a civilization could in principle develop such infrastructure does not mean it will, or that it already has. Now, when people picture interstellar space, they often imagine emptiness so complete that once the propulsion problem is solved, the rest is simply waiting. But empty is not the same as harmless. Interstellar space contains gas, dust, radiation, and the long-duration wear of time. At ordinary speeds, these things may seem negligible. At relativistic or near-relativistic speeds, they become central to mission design. Consider dust. A tiny grain drifting between the stars sounds trivial until you remember relative velocity. At very high speed, even a small particle carries destructive impact energy. Researchers studying probe concepts around 1c, including the work by Crawford on local interstellar medium properties, and direct experimental simulation work by Higgins, do not treat dust as a footnote. They treat it as a serious design issue. A craft moving at that speed cannot casually brush off the medium it crosses. The grains are sparse, but at 1/10 light speed, each collision is upgraded by the velocity to an event that can erode or penetrate structure. Think about what this means practically. A craft on a 50-year crossing to Proxima Centauri does not encounter one dust grain. It encounters many. The number encountered grows with the cross-sectional area of the craft and the length of the path. Larger missions are harder to shield, not only because their mass is greater, but because their surface area is greater. Every cubic centimeter of inhabited volume that faces the interstellar medium is another surface to protect. Shielding is not decorative. It becomes part of the mission's core mass and geometry. But shielding adds weight. Weight increases propulsion demand. More propulsion may demand more structure, more energy handling, and more vulnerability elsewhere. The whole mission starts to feel like a machine built to protect itself from the consequences of being the machine it needs to be. Crawford's review of the interstellar medium makes clear that even at probe scales, the dust and gas environment of the local interstellar medium is a real constraint, not a hypothetical future concern. To get a concrete sense of the impact energy problem, imagine an interstellar probe moving at 1c 1/10 of the speed of light. At that speed, a speck of dust with a mass of just 1 microgram hits with roughly the kinetic energy of a rifle bullet. 1 microgram. That is not a grain of sand. It is a particle invisible to the naked eye. But at 1/10 light speed, that invisible speck carries impact energy on the scale of a projectile weapon. And the interstellar medium, sparse as it is, contains many such particles per cubic centimeter, not one per square meter, not one per cubic kilometer, but spread across the vast volumes the craft must cross. Over 50 light-years of travel to even a modestly distant star, the total number of dust encounters is not negligible. Engineering responses exist in principle: ice shields, magnetic deflection, aerogel-style absorption layers, or simply shrinking the cross-section of the craft as much as possible. But each response has a cost. Shields add mass. Magnetic deflectors require power. Minimized cross-section means minimized capability. These are not imaginary problems that vanish with better engineering. They are real constraints that shape the mission architecture from the ground up. And the constraint does not only come from dust. Neutral hydrogen atoms are present at a density of roughly 1 per cubic centimeter in the interstellar medium. At 1c, a craft sweeping through space is effectively flying into a thin hydrogen wind. The interactions may seem negligible individually, but the cumulative effect over years and decades of flight is erosion, ionization, and radiation from the resulting particle cascades. The shield must handle not just large rare impacts, but persistent low-energy bombardment from the medium itself. Every material solution introduces its own durability question over mission timescales. Radiation raises a related problem. Spacecraft already face radiation damage within our own solar system. Electronics degrade, materials age. Sensitive components require protection. Over long interstellar durations, radiation is not a brief storm to ride out. It is a persistent environment. For hardware, that means cumulative wear and increased failure risk. For biological passengers, if any are present, it becomes even more severe. Shielding enough for life is a far more punishing requirement than shielding enough for instruments. The radiation environment beyond the heliopause, the outer boundary of the Sun's influence, is dominated by galactic cosmic rays, which are high-energy particles accelerated by supernovae and other energetic events elsewhere in the galaxy. These particles penetrate almost any reasonable shielding thickness at energies relevant to crewed missions. They induce secondary radiation when they hit shielding material, meaning that more shielding sometimes creates additional hazard rather than reducing it past a certain point. For uncrewed probes, radiation-hardened electronics can mitigate some concerns over limited timescales. For missions lasting decades, the accumulated damage to components not specifically designed for this environment is a compounding problem without clean solutions. And then there is the quiet tyranny of reliability. Long missions do not merely demand successful launch and cruise, they demand that systems remain functional after decades, perhaps centuries, perhaps longer, with little or no possibility of rescue. Every valve, processor, seal, circuit, sensor, and structural element becomes part of a chain that must not fail beyond what the design can tolerate. Redundancy helps, but redundancy adds mass. Repair helps, but repair systems add complexity. Simplicity helps, but simple machines may be less capable. Interstellar travel forces these tensions to coexist for very long periods. And unlike missions within our solar system, there is no mission control that can dispatch a repair crew, send replacement hardware, or redirect the probe to a backup objective if a key system fails. This is why long mission times are not only psychologically difficult or culturally difficult, they are mechanically dangerous. Time is an adversary. Even if no single hazard destroys the craft outright, accumulation can. A small rate of failure integrated over a long enough interval becomes a major threat. Look at this from the perspective of probability. Suppose a critical system has a very low failure rate per year, say 1 chance in 1,000 of failing in any given year. Over 10 years, the probability it survives is about 99%. Over 50 years, the probability drops to about 95%. Over 100 years, it drops to about 90%. Add 20 such systems, each independent, and a 100-year mission has only about a 1 in 8 chance of all 20 surviving. These numbers are illustrative, not exact, but the principle is real. Long missions accumulate risk in ways that short missions do not. This probabilistic accumulation has a name in reliability engineering. The reliability bathtub curve describes how system failures cluster at the beginning of a device's life, drop during a middle period, then rise again as components age past their design lifetimes. Interstellar missions, by virtue of their extreme duration, force every system well into the right-hand tail of that curve, where failure rates are rising. Designing around this requires either building to radically extended lifetimes, incorporating very aggressive repair capability, or accepting a rising probability of partial failure, none of which is free. The faster the craft, the greater the collision risk per encounter. The slower the craft, the longer the mission, the more years for cumulative degradation. There is no perfect zone where both problems disappear. This is the kind of constraint that engineering sometimes calls a design envelope boundary, a region in the parameter space where every direction away from some central trade-off point makes at least one thing worse. On one axis you have speed, which improves transit time and worsens collision risk. On another axis you have mission duration, which worsens degradation and institutional endurance. The designer must pick a point in that space that minimizes the worst outcome across all dimensions. But there is no point where all the outcomes are acceptable. Every design choice is a trade-off between types of risk, not an escape from risk. What is particularly unforgiving about interstellar missions is that the design envelope is poorly bounded at the optimistic end. In ordinary engineering, we often know that throwing enough resources at a problem eventually produces a workable solution. For interstellar missions, the addition of resources can paradoxically increase certain risks. More shielding means more mass, which means more propulsion requirement, which means more structure, which means more surface area for impacts. You cannot simply spend your way to safety in every dimension simultaneously. Fast travel intensifies impacts. Slow travel intensifies duration. The universe offers trade-offs rather than relief. And there is one more dimension of the survival problem that rarely gets enough space in popular discussions. The question of what happens if something significant breaks, but not catastrophically. A catastrophic failure ends the mission outright. A significant non-catastrophic failure may be worse in one sense, because the craft continues operating but in a degraded state. It may be navigating with reduced precision. It may have lost some of its communication bandwidth. It may be managing its power differently. The cascade effects of partial failures in interconnected systems are notoriously difficult to predict and can produce outcomes more severe than the original failure alone. Mission history is full of cases where a small degradation in one system created unexpected stress on a connected system, which produced a larger degradation, which eventually became a mission-limiting event. Over decades of interstellar transit, the probability that some chain of this kind will play out is not negligible, and the response options available to an uncrewed craft with no ground control capable of timely intervention are narrow. Now imagine scaling all of this upward from a probe to a crewed vessel. A tiny probe may perhaps be armored at the front, instrument-packed, and launched with a tolerance for sacrifice. But an inhabited craft is different. It is not enough for part of it to survive. Its environment must remain stable, breathable, livable. Redundancy must extend across biological systems. Medical problems become design problems. Shielding becomes habitat. Reliability becomes society. So survivability is not a separate topic that comes after propulsion. It is an interlocking constraint. Every engineering choice that improves transit time worsens survivability or demands still more mass to compensate, which in turn worsens energy requirements. The machine cannot be optimized in any one dimension without driving costs upward in others. There is also a material science angle that rarely receives sufficient attention in popular discussions. The interstellar environment subjects materials to a regime of conditions that cannot be fully tested on Earth or in Earth orbit. The combination of cosmic ray bombardment, extreme cold, vacuum-induced outgassing of certain materials, long-duration mechanical stress from the structure's own mass, and the absence of any repair opportunity creates an environment unlike anything in our engineering experience base. Materials that perform well in Earth orbit for a decade may behave very differently over interstellar decades. Polymers degrade, metals develop microstructural changes, lubricants evaporate or polymerize, electronic components accumulate single-event upsets from radiation, seals and gaskets fail with time and thermal cycling. The difficulty is that we have no empirical data on how materials perform in these conditions over relevant timescales. We have extrapolations from shorter tests, we have models, we have educated guesses, but the actual behavior of a structure and its components after 30 or 40 years in the interstellar medium, exposed to the full cosmic ray environment without the protection of a stellar magnetic bubble, is not something any existing test has validated. The mission designer must commit to assumptions about material performance that may be untestable before launch. There is a famous maxim in engineering attributed to various sources. You do not know what you do not know. The surprises in long-duration engineering have consistently come from failure modes that designers did not anticipate, not from failures that were anticipated and avoided. Interstellar missions, by their nature, place a craft in conditions with very limited empirical precedent. The things designers do not know they do not know about long-duration interstellar material behavior represent a genuine category of risk that is very difficult to quantify or design against. None of this is a reason to conclude that no mission can survive an interstellar crossing. It is a reason to hold confidence in the survivability of any given mission with considerable humility, and to resist the slide from might be possible to would be easy for a sufficiently advanced civilization. These are not separate problems to be solved one by one and set aside. They are a system of interlocking constraints that must be managed simultaneously throughout the mission for its entire duration. The interstellar environment does not offer intermissions, and we should carry that picture forward. A craft crossing interstellar space is not coasting through emptiness. It is enduring a sustained, multi-decade assault of low-level hazards, radiation and wear. With no option to return, no option to resupply, and no option to hand the problem to a repair crew. These are not reasons to say Starflight is forbidden forever. They are reasons to say that arrival is not a simple matter of choosing a destination and waiting. A craft may survive launch, survive acceleration, survive the medium, survive time, and still not have solved the hardest part. Because reaching another system at speed is not the same thing as meaningfully arriving there. Now suppose a civilization does the astonishing thing. It builds a probe capable of crossing interstellar space in a few decades. It survives dust. It survives radiation. It stays on course. What happens next? If the probe simply rushes through the target system at a huge fraction of light speed, it may gather fleeting data, perhaps send home a compressed burst of observations and vanish into the dark. That is impressive. It is also not what most people mean by arrival. Arrival implies some form of controlled presence. It implies precision navigation, useful operations, possibly orbital insertion, perhaps landing, perhaps long-term observation, maybe even interaction, and all of that raises a brutal new requirement. The craft must slow down. Deceleration is often the forgotten half of interstellar travel. Accelerating to high speed is difficult enough, but unless the mission is content with a rapid flyby, braking can be just as hard, and sometimes harder, because the vehicle is far from home and can no longer rely on the same infrastructure that launched it. NASA mission concept work on interstellar deceleration exists precisely because this is recognized as a major unsolved engineering challenge. Even when the research is framed optimistically, the conclusion is that arrival science becomes much more valuable once a craft can brake, and that braking multiplies mission complexity. Some proposed ideas for handling deceleration involve carrying propellant, which immediately adds to the mass burden at launch. Some imagine magnetic sails interacting with the destination star's wind. Some examine multi-stage architectures. The details vary, but the message is stable. A useful mission must solve arrival, not just transit. Think about what a meaningful mission to Earth would actually have to accomplish if we reverse the perspective and consider it from the alien side. First, the mission must notice us. Our most detectable signals have existed for barely more than a century. Even those signals grow harder to detect with distance. A civilization would need to identify our world as interesting through biosignatures, technosignatures, or some prior survey strategy, which already narrows the field of likely target selections. Second, the mission must be designed not merely for crossing interstellar space, but for the specific problem of our solar system. Earth is not a point target. It is a moving world orbiting an active star inside a planetary system with gravitational influences from multiple large bodies. If the mission aims only for observation, the requirements are one thing. If it aims for orbital insertion, atmospheric sampling, surface arrival, or anything involving direct interaction, the requirements multiply. Third, the mission must survive the crossing without timely rescue or correction. We have already discussed dust, radiation, and reliability in isolation. But the key point when considering a deliberate mission to a specific target is cumulative. An alien craft reaching Earth would represent a successful completion of a very long causal chain: propulsion, navigation, launch, cruise survival, course correction, arrival, and local operation. Each link adds ways to fail. Fourth, unless the mission is content with a fly-through, it must manage deceleration or local maneuvering. An object arriving at extreme speed without braking may pass through the solar system once and leave. That is not the same as visiting Earth. To do something richer, the craft must slow, turn, or stage its arrival in the inner solar system. And fifth, if any form of interaction is intended, the mission must deal with uncertainty about us. Even if a civilization detected our presence and launched a mission, by the time the mission arrives, 50 years, 100 years, or longer after launch, Earth may be different. The signals that triggered the mission may belong to a past civilization version. The technology that was detectable may have evolved or gone quiet. An interstellar mission is always sent toward a future, not a present. That lag cannot be closed. This is one of the most underrated barriers in the full question. To launch an interstellar mission to another civilization is to act on stale information by necessity. Even if you detect signs of life, by the time the mission arrives, that life may have transformed. That makes the act of reaching Earth not just an engineering venture, but a gamble on how stable a target civilization remains over the mission duration. Navigation alone becomes extraordinary over these distances. The craft must maintain or correct its trajectory across years or decades, often with limited ability to receive timely instructions. With multi-year communication delays, no distant civilization can drive the mission moment by moment. The craft must interpret circumstances locally. It must recover from anomalies locally. In other words, a successful interstellar mission is not just a fast object. It is a highly reliable autonomous system that remains competent after a very long, unsupported journey, with no one able to help when things go wrong. And here is a dimension of the autonomy requirement that becomes increasingly important the closer the mission gets to its target. The target is not passive. A living planet with an active civilization, if that is what has been aimed at, is a complex and dynamic environment. An automated system that has spent decades in transit must suddenly transition from a long quiet cruise phase to a complex local operations phase. It must identify what it is looking for amid background complexity. It must decide what constitutes the mission objective given whatever conditions actually exist. It must handle unexpected situations, a different orbital configuration than expected, different electromagnetic environment, different surface conditions, with the judgment of a competent field scientist rather than a pre-programmed checklist. The gap between a machine that can survive a long cruise and a machine that can then competently navigate the complex local environment of a target star system, make scientifically sound decisions, and take useful action is not trivial. It represents a level of general-purpose autonomous capability that we are only beginning to approach in laboratory settings, and that has never been tested under the conditions such a mission would actually face. Think of the difference between a very sophisticated chess-playing program and a system capable of wandering an unknown city, identifying something interesting, deciding whether it is worth investigating, and reporting back coherently. The first problem, however complex, is bounded and well-defined. The second requires general situational awareness, adaptive decision-making, and judgment under uncertainty. Interstellar arrival science is much more like the second problem than the first. This is not a theoretical future concern that will clearly yield to continued computing progress. It is a fundamental shift in what we are asking a machine to be capable of, and the bar it sets may be as hard to meet as any of the physical challenges we have discussed. Combine that autonomy requirement with the navigation precision required to approach a specific small planet in a populated star system after decades of free flight through interstellar space, and the requirements picture for a meaningful interstellar mission to Earth becomes clear. This is not a single hard problem. It is a dense cluster of hard problems that must all be solved simultaneously by one system operating alone, far from any assistance. So the chain of conditions required for meaningful alien arrival at Earth is long. Notice something. Decide it is worth the cost. Design a mission for the specific target. Build sufficient infrastructure to launch. Survive transit. Navigate accurately. Solve deceleration. Operate locally with high autonomy. And have the target still be worth visiting when the journey ends. That is not a list designed to seem discouraging. It is the honest list. Each item is real. Picture that chain as a filtering sequence. At each step, some fraction of possible missions fail to proceed. The mission is not launched because funding collapses, or the mission is launched but does not survive the crossing, or it survives but cannot break, or it breaks but arrives at the wrong location, or it arrives at the right location but finds that conditions changed, or it finds conditions as expected but lacks the autonomy to act usefully. Each filter reduces the probability of final success from a number that may already be small at the first filter to something considerably smaller at the end. This does not mean arrival is impossible, but it does mean that imagining alien arrival as a routine or easily achieved outcome requires that every one of those filters consistently let missions through, which in turn requires strong confidence about each step that the evidence does not yet support. There is also something to be said about what reaching Earth would actually look like from the perspective of the arriving craft. Our planet is not particularly conspicuous at interstellar distances. It is not the largest object in the solar system. It does not emit strong radiation in most bands. It is one of several rocky objects orbiting a fairly average star. Identifying Earth as the specific target of interest among the solar system's contents, rather than merely using the Sun as a navigational anchor, requires a level of prior knowledge about our world that is far from guaranteed. A mission aimed vaguely at our star would face the problem of finding us specifically, and finding us means locating a small, relatively quiet planet among 8 others, and deciding it is the one worth approaching. None of this is insurmountable in principle, but none of it is free either. A civilization would need not only the power to launch such missions, but the patience to wait decades for outcomes. The industrial will to fund ventures whose returns arrive far beyond ordinary planning horizons, and the deliberate choice to aim them at inhabited worlds rather than merely scientifically interesting ones. Every requirement added is a filter reducing how common this outcome can be, and there is something revealing in the structure of that list. We tend to think of the hard parts of interstellar missions as technical, propulsion, shielding, navigation. But the chain of requirements reveals that social and institutional factors are just as constraining. A civilization must decide that such a mission is worth doing. It must sustain that decision across the decades required to build, test, and launch. It must then sustain funding and attention across the decades of the mission itself, during which it produces no immediate return. It must maintain the institutional memory to interpret whatever the mission sends back when it finally arrives. And it must do all of this through whatever political, economic, and cultural turbulence occurs in the interval. We have difficulty sustaining very long horizon projects even when they produce clear value. Fusion energy research has been ongoing for more than half a century. Proposals for truly large space telescopes have been planned and replanned for decades. Projects with 15 or 20-year development timescales regularly encounter midpoint reassessments, funding interruptions, and scope revisions. These observations are not an indictment of any particular civilization's commitment. They are a reflection of how difficult it is for any long-lived institution to maintain singular purpose across changing circumstances. An interstellar mission launched in one era must be designed by people who will not live to see the result, sustained by people who did not design it, and interpreted by people who barely share a culture with those who designed it. That is not impossible, but it is an institutional challenge as severe as the engineering challenge, and it is rarely included in casual assessments of why aliens would naturally show up here. Now reverse the perspective again. Suppose an alien civilization resolved all of those problems and launched a mission toward Earth. The mission is designed, funded, and operating. The craft is en route. What is it actually seeking? If Earth was targeted because of biosignatures, detectable atmospheric chemistry suggesting life, then the mission was launched before it had any evidence of intelligence. The mission would arrive hoping to find the life its designers inferred, with no guarantee that life has not changed beyond recognition in the interim. If Earth was targeted because of techno-signatures, detectable electromagnetic emissions from intelligent civilization, then the mission was launched based on signals that left Earth decades or more before the mission arrives. The Earth the mission finds is not the Earth its designers observed. It is a later version that may look quite different. Our most powerful early radio transmissions were broadcast in the mid-20th century. A mission launched from a nearby star upon detecting them would arrive at Earth sometime in the 21st or early 22nd century, and what it finds would bear little resemblance to the civilization that generated those signals. Now, every honest analysis of a difficult problem has to meet its best objections squarely, and the idea of practical isolation from other civilizations has real counter-arguments. Not fantasy objections, not simple misunderstandings, genuine counterpoints grounded in physics and engineering logic that deserve to be taken seriously and answered with care. So let us do exactly that. The first counter-argument is tiny relativistic probes. This is a valid and important challenge to any version of this argument that drifts toward absolutism. If a civilization can send a very small, very fast robotic probe on a one-way journey, then some of the most severe constraints we have discussed do become easier. A wafer-scale probe does not carry life support. It does not carry a crew. It does not require the enormous ecological stability, food and water cycling, medical infrastructure, or psychological continuity that inhabited travel demands. It can be made far lighter, which makes the propulsion cost at least imaginable. This is precisely why concepts like Breakthrough Starshot, a project aiming to develop Gram-class laser-propelled probes and drive them toward Alpha Centauri at a substantial fraction of light speed, are taken seriously by working scientists. The Lubin roadmap for interstellar flight lays out exactly this kind of architecture, with enormous directed energy arrays providing the propulsion rather than carried fuel. We are not dismissing the idea. The idea is real, but notice what a tiny relativistic probe actually accomplishes. At its most optimistic, it represents a small, probably one-way, probably non-decelerated fly-through of a target system. The data it returns is valuable. It may survive the crossing intact, but it is not the same as arrival in any inhabited or operational sense. A civilization sending such probes is not sending ambassadors, it is sending fast cameras. And a probe capable of more, of braking, loitering, operating in the target system, responding to what it finds, possibly landing, carries far more mass, which drives all the old penalties back upward. The chain of requirements for a probe that truly operates at a target destination is longer than the chain for a probe that merely passes through. There is also the question of what such a probe tells the receiving end. A fast robotic object reaching our solar system would almost certainly be detectable only by chance, or by design, if it carries some kind of signal or beacon. And even then, meaningful exchange requires either long-duration communication across light years, or direct interaction with materials the probe carries. At the velocities most such concepts assume, the craft and its cargo represent a passing event, so tiny relativistic probes are a genuine weakening of the absolutist claim. They are not a refutation of practical isolation. The second counter-argument is generation ships and suspended animation. Generation ships are vessels large enough and long-lived enough to support a population through a voyage measured in centuries or millennia. Suspended animation concepts are attempts to put biological travelers into a kind of managed metabolic pause long enough to survive the journey. Both ideas are logically coherent in the sense that no single law of physics appears to forbid them at the level of principle, but both approaches trade one set of problems for another. Generation ships do not accelerate to high speeds. They often contemplate slower journeys at fractions of a percent of light speed, which means travel times of thousands of years even to the nearest stars. That makes the survivability problem, which we have already discussed, not a 50-year concern but a multi-millennium concern. Every reliability argument about cumulative failure rates, radiation exposure, and resource management becomes far more severe. Every social and biological argument about maintaining purpose, governance, genetic diversity, and institutional continuity across dozens of generations becomes a new engineering problem in its own right. Suspended animation confronts a related version of the same difficulty. If biology can be truly paused for centuries, a hard assumption that does not yet have any experimental basis at the scale required, the craft's mechanical and structural systems are not paused. They continue to age, degrade, and accumulate failure. The longer the journey, the more time for unmonitored failure in a craft whose passengers are not in a position to monitor or repair anything. A 1,000-year journey in suspended animation is not more survivable because the passengers are unconscious. It is perhaps more survivable for the passengers if the biology works, while being simultaneously more dangerous for the mission as a system because the machines must endure without any living operator attention. We should treat generation ships and suspended animation honestly. They move the question, not resolve it. They tell us that if we are willing to accept very long timescales, very large infrastructure, very difficult social design, and very aggressive assumptions about reliability, then an interstellar trip could in principle be completed, but they do not represent a comfortable path to routine interstellar travel. They represent the last resort of physics-constrained engineering. The third counter-argument, and the most serious of all, is self-replicating probes. This deserves full attention. A single probe capable of arriving at a target system, extracting local resources, and constructing copies of itself, would not be limited by the cost of any individual launch. It would represent a slow-spreading wave through the galaxy. The original mission cost, paid once, could in principle produce a network of self-propagating explorers without requiring the sending civilization to fund each new step. This is the scenario examined in work by Barlow and others in the SETI and interstellar probe literature. At its most ambitious, a self-replicating probe network launched even at slow speeds could, over millions of years, achieve coverage of a substantial fraction of the galaxy. This is a genuine challenge to simple dismissals of alien presence. If self-replicating probe technology is feasible, robust, and is ever developed by a sufficiently advanced civilization, then the galaxy could in principle be peppered with its products, even without civilization-to-civilization travel in the inhabited sense. The spreading wave does not need to move fast. It only needs to be reliable and patient. And there is a related concept in the inscribed matter literature. Hipke and others have noted that if haste is not a priority, physically sending information embedded in a probe can actually be more energy efficient per bit of information than broadcasting it electromagnetically over interstellar distances. For a civilization that cares more about information transfer than speed, a probe, possibly tiny, possibly slow, may be the rational communication strategy. This does not need to be crude, it does not need to be fast, it simply needs to carry the message and survive. So why are we not surrounded by obvious evidence of such networks? That question is taken seriously in the astrobiology literature, and the honest answer is that we do not have a definitive resolution. Several responses are possible. One response is that even self-replicating probes face engineering challenges that are easy to underestimate. Reliable replication without error accumulation, navigation across multiple stellar crossings, resource extraction from systems that may not offer convenient materials, and the problem of exponential error propagation when copies make copies that make copies. In biological systems, replication errors are managed by evolution, which has billions of years and enormous populations to work with. Self-replicating machines require a different kind of quality control. How that problem is solved in practice may be harder than it sounds in principle. Consider what self-replication actually demands technically. A machine capable of self-replication must carry within it not just functional components, but the manufacturing knowledge and infrastructure to reproduce those components from raw materials extracted locally. It must be a factory as well as a traveler. In biology, the information for this is stored in DNA, and the machinery for executing it is the cell itself, developed over billions of years of evolution. In a machine, this would require a level of miniaturized manufacturing capability that is not trivially scaled down, and an error correction protocol robust enough that 10 copies and 100 copies and 1,000 copies remain functionally faithful to the original. Any systematic bias in copying introduces drift. Over generations, drift can accumulate into deviation. What began as a probe designed by one civilization may gradually become something quite different from the original intent. Barlow's analysis of self-replicating probes in the SETI literature treats this problem carefully, rather than dismissing it. The conclusion is not that such probes are impossible. The conclusion is that they depend on specific assumptions about manufacturing fidelity, resource availability, and error control that may be feasible in principle, but are not guaranteed in practice. Another response is that such probes may exist, and we have not yet detected them because we have not looked systematically, or because they are not optimized to be detectable. This response is not comfortable for anyone who wants a tidy conclusion, but it is honest. A third response connects to the timing problem that comes next. Even self-replicating probes require a civilization to exist at some point long enough to build and launch the first generation. If civilizations are rare in time as well as space, or if their active technological phases are brief, then even this approach may be far less common than a naive calculation suggests. The fourth counterargument is perhaps the most widely felt rather than explicitly stated. It runs something like, an advanced enough civilization would simply find a way. The barriers we describe represent our current understanding, and truly advanced intelligence would operate beyond those constraints. This intuition is understandable but not well grounded as an argument. Advanced knowledge allows us to do things we could not previously do. It does not allow us to violate the laws of nature. It does not convert heat into nothing. It does not remove the inertia of mass. It does not transmit information faster than light. It does not allow structures to endure an infinite number of fatigue cycles. It does not make deceleration free. It does not grant unlimited energy without sources. If you strip away the fantasy and ask what advanced knowledge actually does, the answer is, it lets you solve harder optimization problems, find better trade-offs, build better materials, and understand constraints more precisely. None of that changes the constraints themselves. The galaxy is approximately 13.5 billion years old. A civilization that arose even 1 billion years ago, if it developed self-replicating probes, would have had time to seed the galaxy many times over. If truly advanced technology abolishes the barriers we have discussed, then the question of why the galaxy does not obviously exhibit the products of such technology becomes very difficult to answer. The argument that advancement erases the problem only sharpens the question of where the evidence of advancement is. This is a version of what is sometimes called the Fermi question. If interstellar travel and colonization become natural outcomes of civilizational advancement, and if the universe is old enough that many civilizations should have had this opportunity, where is the evidence? We have surveyed considerable fractions of the sky at many wavelengths. We have not detected obvious signs of large-scale engineering, galaxy-spanning communication networks, or the kind of electromagnetic signatures one might expect from a civilization that has been spreading through interstellar space for millions of years. The absence is not definitive proof of anything, but it is information that belongs in the analysis. Some responses to this argument invoke special assumptions. Perhaps advanced civilizations choose not to expand, or choose to hide, or choose to communicate only on frequencies we have not searched, or choose to use forms of technology entirely unlike ours. These responses may all be true, but notice that they add assumptions. The practical isolation thesis does not need to add any assumptions. It simply takes the known physics seriously and notes that the requirements are very hard. Sometimes the simplest explanation for why we do not see visitors is that getting here is genuinely very difficult, and most missions never complete the journey. What all four counter-arguments share is that they are replies to an extreme version of the original claim, the version that says arrival is literally physically impossible in every case. Against that extreme version, they succeed. But the practical isolation thesis does not assert that extreme version. It asserts that arrival is sufficiently difficult, and the combination of physical, energetic, temporal, and institutional barriers sufficiently severe that the expected frequency of successful arrival at any given world is very low. Against that more careful claim, the counter-arguments are partial answers at best. And here is what all four counter-arguments ultimately do not supply. They do not provide a mechanism by which the barriers we have discussed become routine or cheap. The tiny probe sidesteps some barriers, but cannot achieve meaningful presence. The generation ship and suspended animation scenarios push the survival problem into timescales that make every other problem worse. The self-replicating probe is the strongest challenge, but it shifts the question to one of reliability, error control, and observational absence rather than resolving it. And the appeal to unlimited advancement asks us to accept that the laws of physics become irrelevant at sufficient capability, which is not a principle that has ever been demonstrated for any technology at any scale. These counter-arguments are not straw men. They are genuine partial answers, and treating them as such means acknowledging what they do accomplish as well as what they do not. The scenario where a self-replicating probe launched by an extinct civilization arrives here undetected in the deep ocean or in some asteroid belt orbit is not forbidden. We cannot rule it out, but acknowledging that possibility is very different from concluding that routine interstellar visitation is the natural outcome of civilizational advancement. The space between might have happened once in circumstances we have not detected and would naturally be common given the universe's age is enormous, and the counter-arguments individually and together do not close it. So we carry the counter-arguments forward as a reminder of intellectual honesty. The practical isolation thesis is not a proof of emptiness, it is a calibrated assessment of probabilities under known physics. And under known physics, the most defensible position remains that isolation is the default, contact is the exception, and any particular world, including ours, should expect to wait a very long time for meaningful arrival from elsewhere, if it ever happens at all. Now, it is worth pausing to notice what the counter-arguments collectively accomplish, because taken together they do something important. They confirm that the question cannot be answered with absolute certainty in either direction. They keep the question open. They prevent us from concluding too quickly that visitation is impossible in every conceivable form. And that is intellectually honest. What they do not do is shift the balance of probabilities enough to make practical isolation the unlikely outcome. The default remains hard separation, and the counter-arguments occupy the margins of that picture rather than overturning it. What all four counter-arguments share is that they weaken the simplest versions of the isolation argument without dismantling it. Tiny probes are possible in principle, but they represent narrow, limited presence rather than meaningful visitation. Generation ships are possible in principle, but they require extreme assumptions about duration and endurance. Self-replicating probes are the genuinely open door, but they depend on further assumptions, and their apparent absence already presses back on easy optimism. and pure appeals to advancement are not arguments at all without some description of which specific physics gets overridden and why. None of this means the problem is unsolvable. It means the gap between the theoretical possibility and the practical probability of routine interstellar arrival is very wide, and the widest part may not be engineering at all. It may be time. Now, there is a dimension of the separation problem that is easy to miss in the engineering discussion. Because the engineering discussion tends to focus on machines, how fast, how heavy, how shielded, how long. But machines and civilizations are not the same thing. Machines can in principle endure indefinitely. Civilizations cannot be assumed to do so, and once you bring civilizational duration into the picture, the requirements for meaningful contact between two civilizations become not just spatially demanding, but temporally extraordinary. Think about what contact actually requires. It is not enough for both civilizations to exist somewhere in the galaxy. They must exist at the same time. They must both be in phases where they are capable of sending, receiving, or being detected. And they must be close enough, or sufficiently long-lived in their active phases, that the light travel time between them does not simply outlast one or both parties. Recent work in technosignature research has sharpened this problem considerably. Balbi and Grimaldi published a paper in 2024 examining how technosignature longevity affects the probability of detection. The key insight is not complicated. Imagine civilizations as radio stations. Each one broadcasts for some period of time, perhaps a few centuries, perhaps a few millennia, perhaps longer, perhaps shorter. If the broadcast window is long, the chance that another civilization is still broadcasting when the first civilization's signal arrives after years or decades of travel is higher. If the broadcast window is short, the probability of overlap drops. This sounds abstract until you hold a number in your mind. Humanity has been a technological civilization capable of producing broadly detectable radio signals for barely more than 100 years. In galactic time, that is a blink. The Milky Way is roughly 100,000 light-years wide. If a civilization 30,000 light-years away detected our most powerful early radio signals, they would not receive them for 30,000 years. By the time they could reply, and by the time that reply arrived, humanity will have either collapsed, transformed beyond recognition, abandoned electromagnetic communication, or vanished. The temporal precision required to detect each other and communicate before one or both parties change too much is not merely challenging, it is extraordinary. Balbi and Grimaldi's analysis applies a principle sometimes called Lindy's law, the idea that for certain long-lived things, the expected future lifetime is proportional to the current known lifetime. Applied to technosignatures, this means we cannot assume that detected civilizations are early in very long technological lifetimes. Their first detection may be consistent with them being anywhere in their active broadcast window, including near its end. This is a real statistical constraint on interpreting even the absence of signals or the presence of them. But the timing problem cuts deeper than detection. Apply it to physical travel, and the constraints multiply. If a civilization on the other side of the galaxy begins launching self-replicating probes at their technological peak, those probes will arrive at our region of the galaxy millions of years after launch. At that point, the civilization that launched them may no longer exist in any recognizable form. The probes, if they arrive and operate, are orphaned products of a civilization the universe has already transformed. Any interaction is not civilization-to-civilization contact. It is artifact recovery. This is not a hypothetical designed to seem clever. Civilizational change over the timescales we are discussing is not merely possible. It is essentially certain. Human civilization has changed enough in 1,000 years that a person transported from medieval Europe to today would find the world unrecognizable. In 10,000 years, in 100,000 years, the civilizational structure cannot be extrapolated with any confidence at all. Perhaps technology allows a kind of continuity that historical change does not. But the assumption of stability over millions of years is not conservative. It is extraordinarily optimistic. Now consider what synchronization requires in its strictest form. First, Both civilizations must exist as technological entities at overlapping times, not merely as biological species, as active technological civilizations capable of interstellar effort or communication. Second, both must be in a phase where contact is either sought, permitted, or at least possible. Even if two civilizations simultaneously exist, there is no guarantee that both are looking for each other, or are in a position to engage rather than being consumed by internal crises, resource constraints, or social choices that prioritize other objectives. Third, the light travel time must be short enough relative to both civilizations' active windows that a signal sent during one window has a chance of arriving during the others. For nearby stars, this constraint is mild. For stars across even a modest fraction of the galaxy, it becomes severe. Fourth, if physical travel rather than signaling is involved, the timescale of the mission must not exceed the duration of either civilization's interest in maintaining or interpreting the mission. A probe launched by a civilization that ceases to exist before the probe arrives is an orphan. A probe arriving at a destination whose inhabitants do not recognize or care about it may as well not have arrived at all. This orphaned probe problem is more likely than it might first appear. Consider the age of the galaxy and the likely distribution of civilizations through it. If civilizations arise throughout galactic history and have active interstellar phases of, say, 1 to 10,000 years, which is generous compared to our own current trajectory, then at any given moment, only a tiny fraction of the civilizations that have ever existed are still active. The rest are in earlier stages, in later stages, transformed, collapsed, or simply gone. A probe launched by Civilization A towards Civilization B during A's active window arrives at B's location during a time window that may precede B's intelligence, follow B's collapse, or fall in the blank space between. The probability of arrival during B's active phase depends on the duration of that phase and the mission travel time. For long travel times and short civilizational windows, the probability drops quickly. Balbi and Grimaldi's work on technosignature longevity approaches this from a statistical direction. They note that if we ever detected a technosignature from another civilization, we should not assume the emitting civilization is still active. It could be anywhere within its emitting phase. It could be near the beginning or near the end. Our detection is not evidence of contemporaneous existence. It is evidence of past activity at the distance corresponding to the travel time. The more interesting implication is that long-lived technosignatures are more detectable than short-lived ones, which creates a selection effect. We would preferentially detect civilizations that broadcast for a long time rather than typical ones. This may cause us to overestimate the typical longevity of technological civilizations from any eventual detections. Now apply that logic to physical travel. Even if probes are launched routinely, the probability that a probe sent from a civilization now extinct arrives at a planet currently hosting an active civilization capable of recognizing it is constrained by the overlap between two independent timelines. For nearby stars, the travel time is short enough that some overlap may exist. For distant stars, the alignment required becomes increasingly unlikely. The universe may contain immense numbers of probes crossing immense spaces, the products of civilizations that no longer exist, heading toward destinations that are not yet ready to receive them, or that were long since ready and have moved on. This is why the great silence, the observable fact that we do not see obvious signs of intelligent activity across the sky, can be interpreted not only as evidence that civilizations are rare, but also as a natural consequence of even moderately short civilizational windows. If every technological civilization has an active broadcast or expansion phase lasting a few thousand years, then the fraction of the galaxy's history that any given civilization's products are visibly active is very small. In a galaxy hundreds of millions of years old, short active windows mean that most civilizations' evidence vanishes or fades before other civilizations develop the capacity to detect it. There is a tension in how people commonly think about this. The abundance argument runs, there are so many stars and so many planets that civilizations must exist, and given enough time, someone should have arrived. The timing argument complicates the second half of that reasoning. Even if civilizations exist, the probability that they exist simultaneously with us in adjacent space and are currently in an outward expansion or contact-seeking phase, and have successfully launched probes or signals that have reached us, is a product of several independent probabilities. Each one may be individually reasonable. Their product may be very small. Here is an analogy that sometimes helps. Imagine all the conversations that might have happened, but did not, because the people involved were in different places at different times. Two people might have had a profound friendship or a useful collaboration. But one was born in 1870 and one in 1990. They never shared the same era, or one lived in Japan in the 9th century and one lived in Portugal in the 15th. They never shared the same geography. The potential for contact existed. The actual contact did not. Neither absence is mysterious. Both are simply the consequence of time and space. The universe runs the same experiment at galactic scale, with time scales stretching from thousands to billions of years, and spatial separations stretching from light years to kiloparsecs. The number of potential connections between civilizations that never overlapped in space or time is immense. The number that actually produced contact, by any standard, may be very small. And those that did produce contact almost certainly experienced the full suite of physical challenges we have been discussing, which reduces the set further. And here is the deeper point. We tend to frame the Great Silence as a mystery that requires explanation. But under the timing analysis, it may be the expected outcome of ordinary probabilities. The question is not why is no one here? The question is what would have to be true for someone to be here? And the answer is a very favorable alignment of distance, civilizational timing, mission success, and target stability would have to have occurred and left detectable evidence. When you phrase it that way, the absence of obvious evidence is not surprising at all. It may be exactly what we should expect. And what this means for the search is important. The Great Silence is not necessarily the eerie absence it sometimes feels like. It may simply be the expected output of a universe that generates civilizations in scattered places and scattered times, each existing in its active window and then transforming, declining, or disappearing. The universe we live in may in fact contain life in many places. Those places may simply not overlap with us here, now, in a configuration that produces obvious contact. That is not pessimism. It is geometry and probability applied to time. There is also a softer version of the timing problem that is worth articulating. Even within a civilization's lifetime, the will and capacity to mount interstellar missions may not be constant. We have not maintained a permanent moon base since the Apollo program ended. We have not yet attempted crewed Mars missions, despite decades of planning. The capacity to envision large interstellar programs is not the same as the political, economic, and cultural will to sustain them over the timescales required. An interstellar mission must be designed, funded, launched, and then monitored for decades or centuries by an institution that must survive political change, economic pressure, technological disruption, catastrophe, and shifting priorities. Every year of the mission is another year the sending civilization must remain coherent enough to care. None of these barriers is impossible in principle, but multiply together the number of things that must go right: propulsion, survivability, navigation, deceleration, institutional continuity on the sending end, civilizational continuity at the receiving end, temporal overlap between the two, and you begin to see why meaningful interstellar contact may be extraordinarily rare even in a populated universe. Not because any single barrier is insurmountable, but because all of them must be surmounted simultaneously. So we started this documentary with distance, and from distance we built a picture that kept expanding. The energy requirements are extreme. The survivability requirements are layered and compounding. The counterarguments taken seriously complicate but do not resolve the core picture. And now time and synchronization add a final dimension that makes the problem not just spatially difficult, but cosmically improbable. Here is another way to think about the timing problem that sometimes makes it more concrete. Imagine drawing a timeline of the Earth's history on a long ribbon. The ribbon represents 4.5 billion years. Complex animal life appears somewhere in the last 15% of the ribbon. Human civilizations appear in a distance so thin at the ribbon's end that it cannot be rendered at the scale of the ribbon itself. The period during which we have been producing broadly detectable electromagnetic signals, about 100 years, is vanishingly small compared to the total. Now imagine another civilization existed somewhere in our galactic neighborhood at some point during the full 4.5 billion year history of Earth. Perhaps it arose and flourished for 10,000 years, then declined. Its 10,000 year window of technological activity, placed randomly somewhere on a comparable ribbon, has roughly a 0.0002% chance of overlapping with our current period. For us to be in overlapping windows simultaneously requires a favorable coincidence in time as well as in space. The more typical the civilizational lifetime, meaning the more similar it is to what we observe from the only civilization we know directly, the rarer such overlaps become. None of this proves contact is impossible, but it shows that the intuition "there must be someone advanced enough to reach us" implicitly assumes that advanced civilizations arise and persist on much longer timescales than we have any evidence to expect. Remove that assumption, and the timing problem becomes very severe. Keep it, and you have introduced a major unsubstantiated claim about civilizational longevity that the evidence does not support. When you put all of it together, practical isolation does not feel like a conclusion chosen for pessimistic effect. It feels like the honest answer you reach when you refuse to stop adding up the requirements. Now, let us bring this home. We started tonight with a title that sounded like a verdict, and we immediately complicated it. The physics of known reality does not prove that no object ever launched from another civilization could ever arrive in our neighborhood. The careful version of this idea is not absolute. It is a different kind of claim, and in some ways a harder one to sit with. It is the claim that under known physics, the default condition of the universe may be separation, not because intelligence is rare, and not because civilizations lack ambition or curiosity, but because the distances are so extreme, the energy costs so severe, the survival demands so unforgiving, the timing windows so narrow, and the synchronization requirements so precise, that civilizations may routinely fail to reach each other even when they genuinely exist. The universe may be full of islands, each inhabited, each looking outward, and each permanently surrounded by water too deep to cross before the expedition runs out of either time or purpose. Think about what we have moved through tonight. Distance first. Even the nearest star sits at a gap so vast that our fastest machines would take tens of thousands of years to cross it. Relativity second. The speed limit is structural. Time dilation cannot rescue the full problem, and every approach to the ceiling comes with exponentially growing costs. Energy third. The arithmetic of accelerating mass to useful interstellar velocities is not merely demanding, it reframes what advanced infrastructure would have to look like just to move a tiny payload. Survival fourth. Dust, radiation, long-duration reliability, and the compounding nature of cumulative risk mean that survivability is not a problem to be solved after propulsion, but an inseparable co-constraint. Arrival fifth. Slowing down is as hard as speeding up, and meaningful presence requires not a fast pass through a system, but controlled, sustained, local operation. Counterarguments sixth. Honest treatment of probes, self-replicators and generation ships shows they weaken the absolutist framing, but do not dissolve the practical separation picture. And timing seventh. The synchronization problem may be the harshest filter of all, demanding not merely that civilizations exist, but that they exist at the same moment in adjacent space in compatible phases. Each of those 7 considerations is grounded in physics and evidence available today. None of them is speculation in the ordinary sense. None depends on a pessimistic assumption about intelligence or ambition. Together they describe why the cosmos may be both populated and quiet simultaneously. And here is what that conclusion actually opens rather than closes. It means the question, are we alone? And the question, has anyone reached us? Are not the same question. We may be far from alone in terms of existence, and still be effectively isolated in terms of contact. The universe could be in principle full of life, and a visit to Earth could still be extraordinarily unlikely. Those two facts live comfortably together once we stop assuming that the cosmos is arranged for easy contact. It also means that our own efforts to understand where we sit in the universe are not wasted because we are probably not receiving visitors. The study of biosignatures, technosignatures, atmospheric chemistry across distant exoplanets, the careful cataloguing of stars and systems, all of that is still a genuine attempt to understand whether life is common in the cosmos. Finding evidence of life elsewhere, even without contact, would be a transformation in how our civilization understands itself. The practical isolation thesis does not say life is rare. It says that even if life is common, contact is hard. And perhaps most importantly, practical isolation is not a reason for quietism. It does not say, stay here, nothing interesting is beyond. It says, the universe is much larger than any shortcut, and the honest accounting of its scale is not a defeat but a description. There is a kind of intellectual honesty in taking the size of reality seriously rather than imagining it away. The universe does not owe us convenient distances. It is not arranged to make the stars accessible at our pace. And that fact, strange and somewhat lonely as it may sound, is still one of the most extraordinary facts about where we find ourselves. We are standing on a small planet orbiting an unremarkable star in the outer reaches of one of hundreds of billions of galaxies, able to deduce the laws of physics, measure the distances to other stars, calculate the energy required to reach them, understand the limits of our own technology, and ask whether anyone else is out there doing the same thing. That ability is not diminished by discovering that the distances are unimaginably large and the barriers are genuinely severe. If anything, it makes the asking of the question feel more remarkable, not less. And perhaps the most honest thing we can say at the end of this analysis is that it does not resolve the question of whether we are alone. It resolves a different question, which is whether we should expect to have already been visited under known physics. The answer to that question is probably not. Not because the universe is empty, but because the distance, time, energy, survivability, timing, and synchronization requirements are all genuinely very hard, and they all compound on each other rather than cancelling. That answer, carefully understood, should change how we hold the question of intelligent life in the universe. We should hold it with more patience. We should not expect the answer to arrive in the form of a spacecraft over a major city. We should expect it, if it arrives at all, in the form of an extremely faint signal, a subtle biosignature, a statistical anomaly in an exoplanet's atmosphere, or a persistent puzzle in some observatory's data that eventually resolves into something unmistakable. Those are the forms that contact is likely to take if it ever comes. Not dramatic arrival, quiet evidence. And we should continue looking. Practical isolation is not the same as confirmed emptiness. The universe may still contain other minds, other civilizations, other histories. They may simply be as constrained as we are. That symmetry, the thought that whoever they are, they may be looking out at the same vast dark and drawing the same careful conclusions about the difficulty of crossing it, is not a lonely thought. It is, in its own way, a connecting one. The nearest star is 4.24 light-years away. It will probably not send us visitors. We will probably not send it any in our lifetimes, or in any lifetime we can concretely imagine. But the fact that we can precisely say the number, understand what it means, and care about what lies beyond it, that is worth keeping. Think about what it means that we are even capable of having this conversation. We live in a moment where the physics of interstellar travel is well enough understood to identify the barriers precisely. We can calculate the energy required to accelerate a kilogram to 0, 1c. We can model the dust impact hazard. We can estimate civilizational overlap probabilities. We can describe the deceleration problem quantitatively. That level of precise understanding of why something is hard is itself an extraordinary scientific achievement, one that our predecessors even a century ago could not have accessed. So what we are left with at the end of this analysis is not a closed door, it is an accurate map of the terrain. The terrain is very difficult, the barriers are real, but now we know what they are, and knowing what they are is the precondition for any serious attempt to understand what lies on the other side of them. We have not been visited. Under known physics, the reasons why are not mysterious. They are simply very large, very cold, and very patient, and the universe, enormous and indifferent, and quietly full of whatever it contains, continues without particular concern for our arrival timeline.